the let me see the notification that okay, so the recording has been started. All right. So what we were talking about, we were talking about the way we will be conducting this course. So for the theory part, we are two teachers. Myself is Dr. Mazhar Salim, and other teacher is Dr. Safir Abbas. I hope you guys have already taken a class with him, and he would have gone over the course file for this course. There are several basic topics that we will be covering, like shear force diagram, bending moment diagram, calculation of normal stress, shear stress, bending stress, torsion, and columns. The topics that I will be covering with you guys are mainly shear force diagram, bending moment diagram, and deflection. So these are the three things. Or you may say shear force diagram and bending moment diagram is one topic. So mainly we'll be talking about two topics: shear force diagram, bending moment diagram, and deflections. To draw shear force diagram and bending moment diagram, there are two different methods. One is detailed method by writing down equations, and other is direct method or area method. We will be covering both the methods, and we will solve several problems using both the methods. Similarly, for deflection calculations, we have different methods. There are three methods actually, and we will be discussing all of them, and we'll be solving numerical problems for them. All the topics that we will cover in this subject, either myself or the other teacher, are very basic in nature, and they are fundamentals of engineering. Whatever we'll cover here, you will be applying all those concepts later on in several other subjects, maybe in all of them. So I would suggest and strongly recommend you guys to pay full attention and develop a very good understanding of all these basic concepts. If you have any question at any stage, you can simply raise your hand, and when I give you a go ahead, you can ask your question. I do not mind repeating the things again and again. You can ask me 1,000 times. I don't mind that. And other thing is that you can ask questions during the class, or if you want to ask question individually, we can discuss it at the end of the class. And if you want to set up another meeting, you are always welcome to contact me through my email, and we can schedule a meeting. Let me share my email address with you for your reference.
So did you share the email of today's lecture?
Email of today's lecture? What do you mean by that?
The invitation email of today's lecture, because I didn't receive that.
Oh, I have actually generated the series of lectures at the same time. So I don't know whether you will be getting email every time or not, but the best way to join the lecture is that you go to your calendar in Teams, and if you are a part of this team, you will see a scheduled meeting at this time, and simply click join on that meeting, and you will be here. Okay.
Okay, thank you.
So
Thank you, sir.
I have, okay, you're welcome. And what I have done is I have defined the series of our meeting at the beginning of the semester. So I will not be creating a meeting every time. I'm not sure whether it sends an email every time before the meeting or not. But anyways, the best way is go to your calendar. You will find this meeting there and just join the meeting. Now let me just share my email addresses with you. So I normally use two email addresses. One is salim@email.arizona.edu, and other is my UET's official email address, engrma@uit.edu.pk. So these are my two email addresses. You can reach me through any one of them. Normally I check my email frequently, so I think there should be no trouble contacting me. All right. I think with this, we can start our discussion formally on the topics that we will be covering. So let me switch the camera. Okay. I will be writing down almost everything here, and we are recording the meeting, and these recordings will be available to you later on. But still, I strongly recommend you to make notes of lectures. As I write down here, you also make notes, just the way we do it in class. The teacher is writing on the board and the students make notes. Because when you write down the stuff with your own hands, you develop a better understanding. So I strongly recommend everybody to make notes. Okay. So in our today's meeting, as I said earlier, that we will be reviewing our basic concepts. Some of them we already reviewed in last meeting, but because of low attendance, I will be
Excuse me, sir.
Yes.
सर क्या सर आप हमें सर 2 मिनट दे सकते हैं ताकि सर हम पेन पेंसिल ले आए, कोई कापी पेंसिल वगैरह, ताकि नोट कर सकें.
Okay. Okay. If you don't have it, I can wait for a couple of minutes. Okay. I'll give you 2 minutes.
Okay, sir. Thank you, sir.
All right. So I hope you guys are back with your paper and pencils. So let's start our discussion. First basic concept that I want to discuss is about beams. Throughout this semester, we will be talking about beams all the time, especially the discussion between me and you will be about beams all the time. Shear force diagram, bending moment diagram, deflection, all these things are related to beams. Okay, so first of all, we need to develop a good understanding that what a beam is. So can anybody give us some idea about beam? Anyone? Any volunteer to explain what a beam is?
सर इतना सर पढ़ा कि हमने कि सर हॉरिजॉन्टल बॉडी होती है, रिजिड बॉडी होती है हॉरिजॉन्टल टाइप की.
It's a horizontal rigid body. Okay.
Yes, sir. Used for supporting loads.
Used for supporting loads. That's correct.
Which sports load?
Load. Okay. 48. 148. Raise your hand.
Any structural component that bears load along its perpendicular to its longitudinal axis is called beam.
Any structural member that supports loads perpendicular to its longitudinal axis is called beam. Okay, that's good. That's good. All right. So the definition that rule number 148 gave is almost correct. Totally correct. that beam is a structural member, first of all. There are two types of members, structural members and architectural members. What do we mean by structural members? Structural members are the ones that carry load, that support the structure. They are load-bearing members. So beam is a structural member. Other type of member is architectural members, which are used just for the sake of aesthetics, for the beauty. For example, false ceiling is a good example of an architectural member. It is there just for the sake of looks. So beam is not that type of member. Beam is not an architectural member. Beam is a structural member. So it carries load structure. Beam is a structural member that is subjected to transverse load. Now, what is transverse load? I switch my camera. Okay, so if this is a member, this is the longitudinal axis. What is longitudinal axis? Longitudinal axis is an axis that runs along the length of the member, and it passes through centroid of the cross section. You guys already know what a centroid is. In basic mechanics, you would have studied that. For example, for a rectangle, where the diagonals of the rectangle meet, that is centroid of the cross section. So beam is a structural member in which load is applied, which is subjected to loading transverse to the longitudinal axis. So this is the beam, and this axis is the longitudinal axis. And what is transverse to longitudinal axis? Mean perpendicular to the longitudinal axis, like this. So beam is a structural member that is subjected to transverse load. And under this transverse load, the developed internal forces are bending moment and shear force. So these are two forces. Give me a second. Okay, so there are two internal forces developed in the member, and these forces are shear force and bending moment. Today we will discuss at a later stage what do we mean by shear force and bending moment. But the basic definition of beam, that it is a structural member, it is subjected to transverse load, and as a result of transverse load, shear force and bending moments are developed. And normally, in most of the cases, beams are horizontal. But this is not a necessary condition for any member to be defined as a beam. Beams may have any orientation. Beams may be inclined. For an architect, maybe beams are always horizontal and columns are always vertical. But for civil engineers, this is not true. For civil engineers, the behavior of member is important. If member is subjected to transverse load, means perpendicular to the longitudinal axis, it is a beam. If it is subjected to compressive load, it is a column. Most of the time, columns are vertical and beams are horizontal, but this is not an absolute truth. We may have vertical beams. If we have a vertical member and it has transverse loading, that member will be analyzed and designed as a beam. It will not be treated as a column. So for civil engineers, the structural behavior is more important instead of the orientation. So any member that has lateral load and subjected to shear force and bending moment, that is termed as a beam, and it can have any orientation. So this was the definition of a beam. There are several types of beams. We will talk about those types in a short while. And as somebody said that beams carry load and it transfers the load. So normally beams are provided within or underneath the slabs, and they get the load from the slab and transfer the load to the columns, which is finally transferred to foundations. So beam is a load carrying component, and it transfers the loads from one member to the other member. There are types of beams. We'll discover that in a short while. And then there are some types of supports. Before going to the types of beams, I want to talk about types of supports, because beams are divided into different groups depending upon their supporting condition. So types of supports. Can anybody tell me what are different types of supports? Okay, 148. Please go ahead.
Said there are three main types of sports. First one is hinge sport, ruler sport, and fixed sport.
Okay, that's right. There are three types of supports: roller, hinge, and fixed. And do you have any idea that what is the difference between these types?
Yes, sir. In fixed sport, there are three reactions. It means that movement is not allowed in any direction, while in ruler sport there is only one reaction, and that is perpendicular to the structure supported. While in hinge sport there are two reactions. One is horizontal to the structure supported, and one is the vertical to the structure supported.
Okay, that's right. Good. So there are three types of supports: roller support, hinge support, and fixed support. Roller support is the simplest one. This is roller support, and second type is hinge support, and third type is a fixed support. And as we just said, that roller support can generate only one reaction. Only one reaction, and that one reaction is normal or perpendicular to the supporting surface. Hinge support can generate two reactions: perpendicular to the supporting surface and parallel to the supporting surface. And fixed support can generate three reactions: parallel to the supporting surface, perpendicular to the supporting surface, and a resisting moment. So roller support, one reaction only, and that is perpendicular to the supporting surface. Hinge support, two reactions, perpendicular to the supporting surface and parallel to the supporting surface. Fixed support, three reactions, parallel to the supporting surface, perpendicular to the supporting surface, and a resisting moment. And sometimes students define roller support as the one that can generate vertical reaction only, and hinge support is the one that can generate vertical reaction and horizontal reaction. So this definition is not true in all the cases, because sometimes we provide hinge, roller, and fixed supports in different orientations. For example, sometimes we provide a frame structure like this. We have a fixed support at this end, and let's say we have a roller support at this end. Now, in this case, what do you think? What will be the direction of reaction at roller support? Will it be vertical?
Horizontal.
It will be horizontal. That's right. So in this case, horizontal reaction will be developed at the roller support. So defining roller support as the one that can generate vertical reaction only is not the right way of defining a roller support. Roller support is the one that can generate normal to the supporting surface, and similarly hinge is the one that can generate reaction normal and parallel to the supporting surface. And we also sometimes provide, like we have inclined members sometimes. For example, this situation, we have a hinge support. Now in this case, this will be the orientation of reactions. So defining hinge support as the one that can generate vertical and horizontal reaction is again not the right way. So these are three different types of structures. And how do we provide these supports in real structures? For example, let's say we have a beam here and we want to provide a roller support. So this is how a roller support is provided. Oh, sorry, this line is terminating here. in line with the beam. And this is how we provide a hinge support. So that's a free body diagram. This is a hinge support and this is a roller support. And if we want to provide a fixed support, let me write down that this is roller, this is hinge, and how do we provide fixity? This is how we provide fixed support. But in this case, this column has to be really a rigid column, like a reinforced concrete column. That will have the capacity to hold the beam or the grip the beam in a very firm way, like this, like solid support. So this is fixed support. All right, so this is how these are different types of supports, and this is how we provide these supports in physical structures. Everybody is clear about these different types of supports?
Yes, sir.
Yes, sir.
All right, that is great. If you have any question at any point, simply raise your hand. Okay.
सर
Okay. How? Yes.
सर ये रोलर स्पोर्ट में जो आपने स्ट्रक्चर बनाया है रोलर स्पोर्ट का
Right.
तो
Yes.
इसके अंदर ये रोटेशन में मूवमेंट कैसे प्रोवाइड करेगा?
The point is that this structure, this is the support, and we have only one supporting surface here, so it can provide only reaction here, a vertical reaction in this case. Okay, if this beam has a tendency to move in the horizontal direction, this support cannot restrict that horizontal movement in any case, right? It will simply let the beam slide. And similarly, if the beam has a tendency to bend down like this, so this support does not have any restraint like this, that it can restrict that bending movement. It can resist that rotation. It will simply let the beam rotate at this joint. So in case of a roller support, when we are talking about this orientation, the horizontal movement as well as rotation are allowed. Only we have this surface that can generate a vertical reaction. Whereas in this case, vertical reaction as well as horizontal reaction can be generated. But again, this will not restrict any rotation. It will let the beam rotate. But if we have this type of support, then even the rotation will be restricted. When I say rotation will be restricted, it means a resisting movement will be generated here. Okay, this brings another important point in my mind. Sometimes students think that the beam is rotating here, so there is like a movement is present here, just like this movement. But that is not correct. The beam is rotating, so there is no resisting movement there. When the resisting movement is there, that resisting movement will not let the beam rotate. The beam will remain straight near the support. Rather, after some distance, it will start having that rotation. Okay?
Yes, sir.
All right. So with these types of supports, now let's move to different types of beams. Types of beams. So what are different types of beams that you guys have heard of?
Yes, sir. We know about 3 types of beams. Simply
Okay.
supported, cantilever, and overhanging.
Overhanging. Okay. Any other type? Anybody else? 115.
Sir, propped beam.
Propped beam. Okay. Propped. Okay. That's right. What else? Okay. 148. If you have, like, if you have finished,
Cantilever
just
beam.
lower your hand. 126. What did you say?
Prone cantilever beam.
Propped cantilever beam. Okay. That's right. Okay. Anything else? Any other type of beam that you guys have heard of?
Continuous beam.
Continuous beam, that's right. Continuous beam. Okay, so let's see these types one by one. First type is the most common and the simplest one. That's a simply supported beam. Simply supported beam. So the first type is simply supported beam. And what is a simply supported beam? It has a hinge support and a roller support. Simply supported beam is a beam that has hinge support and roller support. And what next type of beam is a cantilever beam. What is a cantilever beam? Cantilever beam has one fixed support and the other end is free. So this beam is a cantilever beam. Cantilever beam has one end fixed and other end is free. Next type is an overhanging beam. Now, what is an overhanging beam? In overhanging beam, one end of the beam is projected beyond the support. Sometimes even the other end is projected beyond the support. Overhanging beam. So this type of beam in which one end of the beam is projected beyond the support is termed as an overhanging beam. Sometimes this is also referred to as single overhanging beam. And if a beam has overhang on both the sides, that is referred as double overhang beam. So this is overhang beam. Next is fixed ended beam. Fixed ended beam. So next type of beam is fixed ended beam. Fixed ended beam has two fixed supports. Okay. Next type is a continuous beam. Continuous beam has more than one spans. What do we mean by span? Span is the part of beam, length of the beam in between two consecutive supports. If you look at this beam, it has only one span. This beam, although it does not have another support at the other end, but still this part is termed as span of the beam. This beam has one span, overhanging part is another span. This is just an overhang. Fixed ended beam has one span, but what about continuous beam? It has more than one spans, and in this example, it has two spans. Span 1 and span 2. So there are two spans in case of a continuous beam. Okay, I see a question. Let me just finish the last type and then I'll see the message. Okay, the last example is a propped cantilever beam. This type of beam that has a fixed support on one end and a roller support at the other end is termed as propped cantilever beam. This one is continuous beam. Continuous beam. So these are 6 common types of beams that we will be dealing with. If you study literature, you might find some other types as well, but these 6 are common ones. Okay, let me see, somebody has posted something in the chat. Okay, if we get practical examples of beam, we'll get, okay. Yeah, so 116, we'll talk about this. So simply supported beam. Now, most of the beams in our houses, let's say, are simply supported beams. For example, in your room, if you have a beam underneath your slab, most probably that beam is a simply supported beam that has supports only at 2 ends. And as I have drawn one figure here, that if we have this type of arrangement, we have roller support at one end and hinge support at the other end. That type of beam is a simply supported beam. For cantilever beams, now the balconies or shades in your houses are example of cantilevers. This cantilever may be a beam or it may also be a slab. So the shade projecting beyond the roof, like the projected part of your roof beyond the exterior wall, is cantilever part. Similarly, sometimes we have projected slabs and sometimes we have projected beams. So if we have projected beams, those projected beams are example of cantilever beams. Okay. Now these cantilever beams. Okay, is there anything else in the chat? Okay, nothing. So sometimes we have beams or slabs. Okay, sorry, what I just said as cantilever, that is an example of an overhanging beam. The projected part of your roof slabs outside the exterior wall is an example of an overhang. Sometimes we have overhang slabs and sometimes we have even beams underneath those slabs. Those are overhanging beams. Now, in certain cases, the beams do not have continuation in the backward direction. For example, you might have seen pergolas in houses. Those are there for aesthetics, but they support their self-weight. So in that sense, maybe you call them as beams. And they are just projected beyond the wall. Those beams are an example of cantilever beams. And fixed-ended beams. Now, just by looking at any beam, it is hard to say that whether it is fixed-ended or not. For that, we need to see the end conditions. If both the end conditions are like this, that it is a beam at an intermediate story. Let's say we have a 10-story building, and in that 10-story building, we are talking about 6th floor. At 6th floor, we have one column here and another column on the other side, and a beam is supported in between. That beam will have fixed supports at both the ends. But as a beginner at this point, just by looking at the beams, probably it is hard for you to judge that whether it is a simply supported beam or a fixed-ended beam. But I tell you one thing, if a beam is just supported on walls, if there are just 2 walls and beam is resting on that, those walls will not, or even if there is a brick column and there is a brick column present underneath the beam and above the beam as well, that brick column will not provide fixity at the end condition. In order to provide this type of fixity, we need strong concrete columns that have that are properly reinforced, or we might have some steel columns that have rigid connection between the beam and the column that can provide this type of fixity. And continuous beam, so any beam, let's say in your house you have 2 consecutive rooms and a beam is running from one room to the other room and there is one supporting wall in between, that type of beam would be a continuous beam. And propped cantilever beam, in some cases we project the beam beyond the wall, but what happens is that the span of the beam is so large that Beam cannot take care of its own self weight. In that case, what we have to do, we have to provide support at the other end. And if we are providing support at the other end, then that beam becomes a propped cantilever beam. No, it does not remain a cantilever beam. If a support is provided at the other end, it becomes a propped cantilever beam. Okay, so
Excuse me,
is
sir?
it clear? Yes.
सर ये जो सिंपली सपोर्टेड बीम है सर जो आपने कहा कि जो आर्म होता है, लेकिन सर आर्म में तो हम देखते हैं कि दोनों जगह पे सपोर्ट सर एक जैसी होती है, तो सर फिर एक हिंज और एक रोलर कैसे होगी? वो तो दोनों या हिंज होंगी या रोलर होंगी।
Right, your point is valid. Now, as far as the practical conditions are concerned, in reality, when we discuss these things in theory, we, especially at the beginners level, at the level where we are right now, we define the things very discreetly and very clearly. We see that, okay, this is a roller support, it will provide one reaction, vertical reaction in this case only. This is a hinge support and it will provide just vertical reaction and horizontal reaction in this case. But practically that is not the case. In reality, even if we say that, okay, this support is a roller support, even then this support this support has the capacity to generate some horizontal reaction. Why? Because of its self weight. The self weight of the structure is significant, and self weight, and there might be some external load acting on the beam as well. So that will create significant friction at the support level, and that friction will generate the ability in the support to produce horizontal reaction as well. So theoretically speaking, we say that, okay, this is a roller support, but practically this will not behave like a roller support. Rather, it will have some horizontal reaction as well. So in real structures, under practical conditions, when we study the things theoretically, we make some simplifications and we just say that, okay, this is a roller support. This can only generate vertical reaction or reaction normal to the supporting surface. It cannot produce any horizontal reaction, but that's not the case in reality. In reality, even roller supports can generate some horizontal reaction. So the real supports, it's hard to categorize those supports into any one of these categories, like in a very hard and fast manner. It's an approximation that we say that, okay, this support is a roller support or this support is a hinge support. Okay.
सर एक और क्वेश्चन है।
Yes.
सर अगर हमने सर प्रोवाइड ही करनी है सपोर्ट, तो सर हम फिर उसमें ये क्यों गुंजाइश रखते हैं कि वो थोड़ा सा इधर बेंड हो जाए, जैसे आपने कहा कि सिंपली सपोर्टेड में कि वो जो है ना फ्रीली मूव कर सकता है रोटेशन में, तो सर हम इनको रोटेशन क्यों देते हैं? तो हम ये है कि जो स्ट्रक्चर है वो मूव ना करे, बिल्कुल भी जैसे वो है वो स्टेबल रहे।
Okay. Actually, when we say that this support will allow the structure to rotate a bit, those rotations are very small. Like we will talk about stability in a short while. You are 100% correct that we want our structures to be stable. We do not want any excessive movement in our structure. Structure has some deformations or some deflections. In this course, at later stage, we will talk about deflections. So although apparently the beams and slabs and columns that appear to have no deflection or no movement, there is some movement and some deflection in the beams and columns. We will study how to calculate them. So, and now the question is that why don't, okay, let me finish. Why don't we want to completely restrict the movement? The answer is that for that we will have to make special arrangement. And if it is not required, then we do not need to make that arrangement. Okay, let's see. Okay, 116, do you want to say something?
Sir, if a beam is totally fixed, then what will be the effect of thermal contraction and expansion?
All right. if the beam is totally fixed and we do not allow any displacement. Now, one thing is, this is theoretical, that we say that it is completely fixed. Even if we have fixed support, some movement is there, but at this stage we will be assuming that there is no movement. In that case, if we expect any thermal expansion in the beam, then we have to design our structure to take care of those stresses. Right. Let me turn on my other camera view. So if we have this beam, and this beam has two fixed supports, which means that we will not allow this beam to expand at all. It means that when the temperature of the beam will rise, and it will have the tendency to expand. If you let it expand, it is fine. If you do not let it expand, then thermal stresses will be generated in the beam. In this course with Dr. Safir Abbas, we will discuss that how to calculate those thermal stresses. So if we expect those thermal stresses to be generated in the beam, then we have to design the beam for those thermal stresses. Okay, if we do not allow the beam to move under thermal expansion, then thermal stresses will be generated, and we have to design the beam against those thermal stresses, and then the beam can resist those thermal stresses and it will be safe. But if we do not do that, then in that case the beam might show cracking. If the thermal stresses are excessive, the beam will crack. Okay, is that clear?
Yes, sir. Thank.
Okay, you're welcome. 146. I see your hand raised. Okay.
Sir ji, it is compulsory condition for continuous beam to have roller support in between, or it may be any support.
Oh, it may be hinge support, roller or hinge.
Okay.
Okay. So, and even in case of a propped cantilever beam, this support may be a hinge support. Okay, and this structure will still, this beam will still be categorized as propped cantilever beam. Okay. All right. So these were different types of beams. Now, with the types of beams, there is another important concept, that's determinacy and indeterminacy. Have you guys ever heard about this concept? Determinacy
No.
or indeterminacy? Never?
No, sir. We didn't have that.
Oh, never heard that? Okay, that's a bit surprising. But anyways, let's talk about that. Determinate beams are those beams which can be analyzed using the conditions of equilibrium only. If we have a beam that can be completely solved or analyzed using conditions of equilibrium only, that is termed as a determinate beam. I repeat, a beam that can be completely analyzed just by using conditions of equilibrium is termed as a determinate beam. And right now we are just talking about two-dimensional systems. So what are the conditions of equilibrium for a two-dimensional system? If I write down the conditions of equilibrium for a two-dimensional system, conditions of equilibrium.
सर ये दो होंगे सर, एक एक्स डायरेक्शन में सर फोर्सेस जो हैं और वाई डायरेक्शन में फोर्सेस है, ये दोनों ही जीरो के इक्वल होने चाहिए, सम ऑफ इन फोर्सेस का.
Okay. Don't you think that there would be a third condition as well?
थर्ड कंडीशन भी होगी.
movement
वो movement के बारे में.
sum of movement.
वो sum of movements के बारे में. Exactly, that is true. So if I say that these are my three axes, x, y, and z axis. X axis is x and y axis are in plane, in this plane. X is along rightward direction, y is upward, and z is out of plane. Z is basically this direction, out of plane direction. Okay. So if these are three axes, then the conditions of equilibrium are sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. So these are the three conditions of equilibrium for any two-dimensional system. So if a beam can be completely analyzed, using these three conditions of equilibrium, that beam is termed as a determinate beam. So if a beam can be completely analyzed using three conditions of equilibrium, that beam is termed as a determinate beam. So we have just seen that there are three conditions of equilibrium. By analysis of beam, what do we mean? We mean determination of its reactions. Here, by analysis of beam, we mean determination of its reactions. So let's see which of these beams are determinate and which one of these beams are indeterminate. Now, if we look at the simply supported beam, how many reactions will be generated in this case? One reaction, two reaction, and three reaction. So there are three reactions. How many equations are there? Three equations. So can this system be analyzed using these three conditions or equations?
Yes, sir.
Right. Yes, this can be analyzed. We have three unknowns and we have three equations. So this system, simply supported beam, can be analyzed using conditions of equilibrium only. So we will call this beam as a determinate beam. Simply supported beam is a determinate beam. Now next, move to cantilever beam. How many reactions? 1, 2, 3. Do we have any more reactions?
No, sir.
No. 3 reactions, 3 equations. Can this beam be solved?
No, sir.
Yes. No. Why not?
Yes,
Three
sir.
beams, 3 reactions or 3 unknowns and 3 equations. So this
Yes,
system
sir.
can be solved. So this beam is also a determinate beam. Let's move to overhang beam example. How many reactions? 1, 2, 3. 3 reactions, 3 equations. Can this be analyzed or solved?
Yes, sir.
Yes. So this is also a determinate beam. So all these 3 beams that we have shown here are examples of determinate beams. Determinate beams, because these beams can be analyzed using just 3 conditions of equilibrium. Now let's move to the next 3 examples. Next 3 types. Fixed ended beam. Let's count the reactions. 1, 2, 3, 4, 5, 6. So there are 6 reactions and there are 3 equations. Can we solve this system?
No, sir.
No. So this is an indeterminate beam. Let's move to continuous beam. Let's count the reactions. 1, 2, 3, 4. 4 reactions, 3 equations. Can we analyze this?
No, sir.
No, we cannot.
sir.
So this is an indeterminate beam. Let's move to propped cantilever. Let's count the reactions. 1, 2, 3, and 4. 4 reactions and 3 equations. Can we analyze this?
No, sir.
No, we cannot. And when I say that we say we cannot analyze, we mean we cannot analyze just by using equations of equilibrium. So it
Yes.
means that these 3 beams are indeterminate beams. Indeterminate beams. So this is how we decide that whether a beam is a determinate beam or an indeterminate beam. And just for clarity, being indeterminate is not a bad thing. We don't say that, oh, it's an indeterminate beam, so it's an undesirable beam and we do not want to provide it in our structure. No, that is not the case. Being indeterminate means that this beam is relatively difficult to analyze. It cannot be analyzed just by applying these three simple conditions of equilibrium. Rather, we need some more relationships. Okay, so the beams which cannot be analyzed using three conditions of equilibrium are indeterminate beams, and the ones which can be analyzed are determinate beams. Is everybody clear about this?
Yes, sir.
Yes, sir.
Okay, that is great. So if you guys are clear about this concept, now at this point, we can take a break for 10 minutes. And after 10 minutes, we will continue once again. But keep one thing in your mind, that the recording of our session will go on. So if you guys discuss anything or talk to each other, be careful, because everything is being recorded and we will like post it online, so it will be available to everybody. Okay, so the recording is on. I'm here in the meeting. This is a break just to have some water or just to have a little. So we'll start in minutes. It's 10:57. We'll start at 11:07. Okay. So I'll just mute my mic and stop streaming my camera, and we'll meet at 11:07. Okay, guys. So this is 11:07. So let's start our discussion again. Let me share my camera view. Okay, so everybody can see this paper and pencil. My camera view.
Yes, sir.
Yes, sir.
Okay, I could not hear you guys. So can you guys see the screen, the camera view?
Yes, sir.
Yes, sir.
Okay, that is great. All right. So
Excuse me, sir.
let's.
Sir, I have a
Yes.
question.
Yes.
Sir, on which basis we say that this particular beam are indeterminate, like in case of fixed ended beam, we say that here is a rotation, two rotations, and because we have two fixed poles. So why we say that this particular beam has like four equations and like this type of. Can you explain this?
Let's one more time. What is a determinate beam? A determinate beam is the one that can be analyzed just by using conditions of equilibrium. How many conditions of equilibrium are there for a two-dimensional system? Like right now we are talking about two-dimensional systems only. Otherwise, for three-dimensional system we have 6 equations, but we are not talking about that. So we are talking about two-dimensional systems, and for two-dimensional system there are 3 equations of equilibrium. And what are those 3 equations? Sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. So if we have a beam in which there are 3 unknowns, then we can analyze that beam, or we can find out the unknown reactions using these 3 equations. And if that is the case, then that beam is a determinate beam. For example, simply supported beam. 3 reactions, or in other words, 3 unknowns and 3 equations. Okay, so we can analyze the system. From mathematics, we know that we need as many equations as number of variables are there in a system. If we want to find one variable, we need one equation. If we want to find out two variables, let's say x and y, we need two relationships in x and y. If we want to find out three variables, x, y, and z, we need 3 equations to determine those 3 unknowns. So the number of unknowns must be equal to the number of equations we can find the unknowns. For this beam, 3 unknowns, 3 equations, so it can be solved. 1, 2, 3. 3 unknowns, 3 equations, beam can be solved. Overhanging beam, 1, 2, 3 unknowns, 3 equations, so we can solve the system. Fixed ended beam, 1, 2, 3. 3 unknowns here, 4, 5, 6. 3 unknowns on this side, so total we have 6 unknowns. So if 6 unknowns are there, how many equations do we need to solve the system? We need 6 equations. Do we have 6 equations here? No. We have just 3 equations of equilibrium. So in this case, this case is an indeterminate beam. Similarly, this beam, 1, 2, 3, 4 unknowns, 3 equations, indeterminate. 1, 2, 3, 4 unknowns and 3 equations, so it's an indeterminate beam. Okay, somebody has sent something in chat. Let me see what's that. Okay, network issue 150 today's class. Okay, right now, like currently, I'm marking attendances for those students who are here. We'll see what to do with these kind of issues. We'll see that. Okay, is this clear now?
Yes, sir. Thank you, sir.
Okay, you're welcome. And then with this determinate and indeterminate beam, another concept comes that is called degree of indeterminacy. Degree of indeterminacy. if I just abbreviate it as DOI. Okay, degree of indeterminacy. Now, what is degree of indeterminacy? Degree of indeterminacy is the difference between number of unknowns and the available number of equations. So, degree of indeterminacy is equal to number of unknowns or yes minus number of equations of equilibrium. So degree of indeterminacy is equal to number of unknowns or number of reactions minus the number of equations of equilibrium. So for this beam, a simply supported beam, if I calculate degree of indeterminacy, how many unknowns are there? 1, 2, 3. How many equations are there? 1, 2, 3. So what is degree of indeterminacy? 0. And that is why this beam is a determinate beam. Okay, any question? Does anybody want to ask any question? Okay. So degree of indeterminacy, let me see if anybody has raised his hand. Okay, I don't see any hand raised. Okay. So degree of indeterminacy of a simply supported beam is 0, and that's why it is termed as determinate beam. Cantilever beam, degree of indeterminacy. How many unknowns or how many reactions? 3. How many equations? 3. Degree of indeterminacy is 0. Let's come to overhanging beam. How many unknowns? 1, 2, 3. How many equations? 1, 2, 3. What is degree of indeterminacy? 0. So degree of all indeterminacy of all determinate beams is 0. That's why we call them as determinate beams. Next, let's come to this category, this group, which is the group of indeterminate beams. Degree of indeterminacy. How many unknowns are there? 1, 2, 3, 4, 5, 6. How many equations of equilibrium are there? 1, 2, 3. So what is degree of indeterminacy? 3. Okay. Now, what does degree of indeterminacy actually tell us? Degree of indeterminacy actually tells us that how many more number of equations are required in addition to the equations of equilibrium. So when I say that the degree of indeterminacy of a fixed ended beam is 3, by this I mean that I need 3 additional equations other than the equations of equilibrium to solve the system. That is what degree of indeterminacy tells us. For this continuous beam, degree of indeterminacy, how many unknowns? 1, 2, 3, 4. How many conditions of equilibrium? 3. So 4 minus 3 equal to 1. What does this mean? This means that we need one more relationship in addition to the equations of equilibrium to solve the system. Next is propped cantilever beam. Degree of indeterminacy. 1, 2, 3, 4 reactions. How many equations? 3. What is degree of indeterminacy? 1. So this tells us that in order to analyze this propped cantilever beam, we will need one additional equation other than the equations of equilibrium. So this is how we calculate the degree of indeterminacy of any given structure. Anybody having any question about this? If you have any question, raise your hand. Okay, 133, please go ahead.
Yes, sir. Thank you. Sir, as someone already discussed the case of having a similar sort of supports at either end. that be a roller support in a case of a practical problem. So in that case, if we determine the degree of indeterminacy, so that would come out to be -1. So what would we do in that case?
You mean a beam having two roller supports at the ends? Okay, let me show you. Is this the case you are talking about?
Yes, yes, sir. Practically, if we have supports, yes.
All right. So just give me a minute. Let's talk about stability first, and then I'll come to this example, this question. Okay.
All right.
Other than determinacy, another important question about beams is regarding their stability. Stability. This is it. Okay. What do we mean by stability? It means that under the application of load, like the beam or the structure, the supporting system should be sufficient, or sufficient reaction should be there so that the structure remains stable. It does not like slide off the supports. There are two conditions of to make sure the stability of any structure. First condition is there should be at least 3 reactions. This is first condition of stability. Second condition of stability is all the reactions should not be parallel to each other. These are the two conditions that must be satisfied for a beam in order to be stable. There should be at least 3 reactions, and all these reactions should not be parallel to each other. Now let's look at these examples, these types of beams that we just discussed, that whether all these beams are stable or not. We have 1, 2, 3 reactions. These two are parallel. The third one is not parallel. So this beam is stable. Okay, so we are good. This beam is stable. We are not talking about determinacy or indeterminacy. Okay, 1, 2, and 3 reactions. 3 reactions. First condition is satisfied. All of them are not parallel to each other. So this is stable. 1, 2, 3 reactions. 2 are parallel. Third one is not parallel. So this is a stable beam. Okay. 1, 2, 3, 4, 5, 6, 6, and all of them are not parallel to each other. Stable. 1 both the conditions are satisfied. This is the stable beam. Propped cantilever beam. 1, 2, 3, 4. These vertices are parallel to both. Okay, so I did it. See, are indeterminate. All of I said it's a bad beam, an undesirable beam, because this one is an indeterminate beam. No, that's not the case. But stability is desirable attribute we do not want our structures to be unstable. If our structure is unstable, we need to change it. Okay.
सर आपकी सर आवाज़ नहीं आ रही सर, डिस्टॉर्टेड है सर, बहुत ज़्यादा डिस्टॉर्शन आ रही है सर, बहुत ज़्यादा।
जी सर बिल्कुल समझ नहीं आ रही, बहुत ज़्यादा डिस्टॉर्टेड है।
Okay, so I have changed my network. Is my voice clear now?
Yes sir, it's clear
Yes,
now,
sir.
but sir we can't
Yes, sir.
hear anything before.
यस सर अब क्लियर है।
Before? Okay, no problem. I'll repeat this stability thing. Okay. So
Yes sir.
these structures, I said that there are two conditions of stability. First condition of stability is that there should be at least 3 reactions, and second condition of stability is that all of those reactions should not be parallel to each other. Here I have seen or checked that whether that condition is satisfied for all these different types or not. We have 3 reactions and all of them are not parallel to each other. So this is okay, stable. 3 reactions and all of them are not parallel. So this is stable. 1, 2, 3 reactions and all of them are not parallel. So this is stable. Fixed ended beam. 6 reactions and all of them are not parallel. So this is also stable. Continuous beam. 1, 2, 3, 4 reactions. All of them are not parallel. So this is stable. Propped cantilever beam. 1, 2, 3, 4 reactions. All of them are not parallel. So this is also stable. So these 6 types of beams that we discussed before are all stable. And I was saying that stability is a desirable attribute of our structure. We do not want unstable structures. If we are designing a structure and we find that the structure is unstable, we need to change that. We need to make it stable and we need to satisfy the conditions of stability. So now, if I come back to the question that was asked previously about this beam, that we have a beam that has 2 roller support, and if we calculate its degree of indeterminacy, 2 reactions, so degree of indeterminacy is equal to 2 unknowns minus 3 equations equal to -1. Actually, in this case, the degree of indeterminacy does not matter, because this is the structure is unstable. We need to make it stable first. And let's say, for the sake of argument, even if we just forget about stability, negative degree of indeterminacy is not a problem. If degree of indeterminacy is 0 or less than 0, that means the structure can be analyzed. It's still okay. Okay, so if I apply a load here, let's say 10 kilonewton. So just by applying sigma Fy equal to 0, I can give you that this load is acting at the center. So 5 kilonewton reaction will be generated here and 5 kilonewton reaction will be generated here. So negative degree of indeterminacy is not a problem as far as the determinacy or indeterminacy concept is concerned, but this structure is unstable and we don't want an unstable structure. So we will modify this structure. And in addition to this, I want to give you another example. Sometimes one condition of stability is satisfied, but the other is not satisfied. For example, if I give you a continuous beam with 3 roller supports, now how many reactions does it have? 3 reactions. So 3 reactions are there, which means the first condition of stability is satisfied. What about the second condition? All the reactions should not be parallel to each other, but all these 3 reactions are parallel to each other. So although the structure has 3 reactions, but it is still an unstable structure. If I apply an inclined load having vertical and horizontal components, the structure will slide over the supports, and it will finally be destabilized. So is this clear now?
Yes, sir. Clear.
Okay, that is good. If anybody has any question, you can raise his hand.
Sir, one more question that arises in my mind since you've mentioned this concept of parallel reactions.
Okay.
Sir, hypothetically, if you are to say that these reactions are acting against each other, as in they are cancelling out each other. Can there be any such case?
Cancelling out each other. Actually,
Yes.
what will be the direction of reaction? That depends upon the applied loading. We cannot ourselves introduce any reaction, right? Reaction is the result of action. So in some of the conditions, we will see that it depends upon the applied loading. Under certain conditions, we will see that at some of the supports, there will be reactions in the downward direction. So this
Yes,
will
right.
happen, okay? Some upward reaction and some downward reaction. But if we have satisfied the conditions of stability, then the applied loading and these reactions will be finally balancing each other, and the structure will remain stable. So upward and downward both reactions will be there, or may be there, depending upon the nature of the applied loading. When we are doing this general discussion, every time I draw reaction in the upward direction, and for a hinge support, maybe when I draw reactions, I draw one upward and one rightward, for roller one upward. But actually, I always draw these directions like hypothetically. In reality, I don't know what will be the direction finally. For example, on this structure, if we apply an upward load, then both these reactions will be in the downward direction. So the nature or the direction of these reactions depend upon the nature of applied loading. And at this point, we are not considering the loading, so we cannot comment on that. But when we will have the loading with us, when we'll be solving the complete problem, then in some of the cases, we will see that at one roller support, the reaction will be upward, and in other roller support, the reaction will be downward. It will happen. Okay.
But sir, in such case, wouldn't that beam would be acting as in the reactions of gravity, and wouldn't that make a bit more susceptible to instability?
No, as long as the supports do not fail, because
Right.
there is another parameter that is about the strength of the support. For example, I'm saying, okay, hinge support is there. It can generate vertical reaction and horizontal reaction. That's fine. But it does not mean that it can generate infinite magnitude of horizontal and vertical reaction. It will have certain capacity. Every structure, every support has certain capacity. And once that capacity is exceeded, the structure fails. That is why buildings and bridges collapse. That's the reason that we load the structure beyond its capacity. So although, like for example, this structure, it can fail under the application of this vertical load. If let's say capacity of this support is to generate 5 kilonewton of vertical reaction and 3 kilonewton of horizontal reaction, that's the maximum magnitude of reactions that this support can generate. If I apply some load for which the reaction here exceeds 5 kilonewton, the structure will fail. Okay?
Yes, right. Sir.
Got it?
Got it.
All right. So this was about the determinacy and stability of the structures. I hope it is clear. Now, after this, let's move to some other small concepts. Beam shapes. Let me give you different beam cross-sectional shapes that we will be dealing with in our discussion during this course. Beam cross-sectional shapes. Okay, there are different cross-sectional shapes of beams. I hope you guys already know what do I mean by a cross-sectional shape. If I draw a member like this, let's say we have one support here and we have another support here. So this axis is termed as longitudinal axis. Longitudinal axis. And if I cut a section here, let's say section 1, so I will see this supposedly. So the shape of the section is rectangular, and this will be the centroid. I'm just telling you the basic terms, which I hope you guys already know, but just to refresh your memory, I'm explaining these things. So this axis is longitudinal axis that runs along the length of the member and passes through the centroid of the cross section. Okay, this is longitudinal axis and this is cross section of the member. Now, under this beam cross-sectional shapes, I want to give you different cross-sectional shapes that are commonly used. Most commonly used shape is a rectangle. You guys would have surely seen rectangular beams in your houses or in other buildings or even in civil engineering building. So rectangular shape. Sometimes we provide T-shape. T-shaped beams. Sometimes we provide I-shaped beams. I-shape is more like a layman language. In civil engineering terms, we call it W section or sometimes an HP section, but you will study that later on. In T section and I section, this vertical segment or element is termed as web of the section, and this horizontal element is termed as flange. So these horizontal elements, two horizontal elements of I section and this one horizontal element, these are termed as flanges, and these vertical elements are termed as webs. Web of an I section, web of a T section, flange of a T section and flange of an I section. Other shapes that we might be dealing with are is box shape. It's a hollow section, but the shape is rectangular. Another section that we might be dealing with is channel section. It is also termed as C section. Sometimes we might also deal with L section. You will surely deal with this L-shaped section sometime, if not in this semester, maybe next semester. But sometimes we do provide L-shaped beams. So these are the common cross-sectional shapes that are used for beam sections. When we will be studying deflection or stresses, we will talk about these shapes. Is that clear?
Excuse me, sir.
Yes.
सर सेंट्रॉइड का सर एक दफा बता दें.
Centroid. I hope you guys would have discussed centroid in basic mechanics. So centroid is basically geometrical center of a shape. Geometrical center of an area is termed as centroid. For a rectangular section, how do we calculate it? The intersection of diagonals is centroid. For a rectangular section, the intersection of its diagonals is its centroid. In basic mechanics, did you guys study the geometrical properties of plane areas? Anyone? In basic mechanics, did you study geometrical properties of plane areas?
नहीं सर,
No,
सर
sir.
हम नहीं सर,
No?
हमने नहीं पढ़ा.
Have you ever heard about centroid, axis of symmetry, something like this? How to calculate first moment of area, how to calculate second moment of area. Have you ever heard about second moment of area?
नो सर.
No,
सर
sir.
हमने सिर्फ सर सेंट्रॉइड और एक और चीज के बारे में, सेंटर ऑफ रोटेशन शायद इस तरह
Center
कोई
of
चीज.
rotation. Okay. Okay. All right. Thanks for letting me know. Although in our discussion regarding shear force and bending moment, we will not need the centroid much. We will need it for deflection probably, but for stress calculation, you will need all these things: centroid, second moment of area, and these concepts are normally covered in basic mechanics. For some reason, you have not studied that, but anyways, when Dr. Safir is teaching you stresses, just let him know that you do not know what centroid and second moment of area is. then he will explain those things to you in a bit more detail. Okay. So these are cross-sectional shape, and simple definition of a centroid, if you do not know, it's the geometric center of a cross-section. And centroid, sometimes it is similar to the center of gravity, but every time that's not the case. If the section is of homogeneous material, then center of gravity and centroid are the same. But if section is of non-homogeneous material, then center of gravity and centroid will be different. Okay, I see a message in chat box. Voice is not okay. This is an old message, I think. 11:22. All right. So centroid. At this point, do you know now what is centroid? Centroid is the geometrical center of an area. For symmetrical shapes, it is simple to calculate or determine the centroid. For example, for a rectangle, as I said, that it is the cross section, the intersection of the diagonals. For triangles, as we okay, we have not discussed the loads yet. For triangles, the centroid is somewhere over here. If this is, I say, height, then this dimension is h/3. And if this dimension is, let's say, b, then this location of centroid is b/3. Okay, so these are the centroids. Now, if you have not studied that, that's a bit surprising for me. But when we'll come across a situation when we'll need these things, we will explain these things in a bit more detail. After the cross-sectional shapes, let's discuss the types of loads. Types of loads. Okay, what are different types of loads? If this is a beam and a load is acting like this, I say load is P and the span is L. So this type of load is termed as point load. Point load is the one that acts at a point. It is concentrated at a single point. In reality, in practical situations, point loads are not concentrated on like a dot. Rather, we have situations like this. If I have a beam and a column is resting over that beam, let's say this is a brick column, and it is resting over the beam. So this column will apply a point load on this beam. And you can see that this the load of the column is not acting at like a single dot. It has certain area, but the point is that the area on which the load is acting is much smaller than the length of the beam or the overall geometry of the problem. That's why we call this a point load. Second type of load is a uniformly distributed load. Uniformly distributed load is like this. Okay, it is distributed over the length or distributing over an area. If this is the span and omega is the intensity of the load, the resultant magnitude of load can be calculated as, the resultant is calculated as omega into L. And what is this omega into L? This is area of this rectangle. So if we have a uniformly distributed load, we abbreviate it as UDL. If we have a uniformly distributed load, then this is represented with a rectangle, and its magnitude or the magnitude of the resultant can be calculated as area of this rectangle, omega into L. And location of the resultant will be the centroid of this rectangle. If the span, this total dimension is L, then this will be L/2. L/2. Another way of representing a UDL is that's a quicker way. Whenever we solve numerical like manually, we just show this type of symbol. That means a UDL. Okay, and in practically in the real structures, if we have a beam and a wall is constructed, a wall of constant height is constructed over that beam, that will be an example of a uniformly distributed load. And the third type is varyingly distributed load. The load that varies along the length. Span is L and we call this VDL, varyingly distributed load. This side is omega. So the resultant of this load is omega L by 2. What I have done here, I have simply calculated the area of this triangle. Omega is the vertical side, L is the length. So omega into L divided by 2. That is the area of a triangle. And as we discussed earlier, the location of the centroid, the resultant of this load will pass through the centroid of this area. And what is the location of centroid for a triangle? From this edge, it will be 2L over 3. And from this side, it will be L over 3. Resultant will pass through this point. And a practical example under which the beam will be subjected to a VDL is if I have some support, let's say a wall or something like that, and there is a heap of sand, let's say, or any other material. We have a wall whose length is not constant, then that type of load is an example of a VDL.
Excuse me, sir.
Okay, any question? Yes.
सर ये रिजल्टेंट का सर हमें डिफाइन करने का क्या मकसद है?
इसका मकसद ये है, under certain conditions we need to know that how much is the total magnitude of load. When we will be studying how to calculate shear force, how to calculate bending moment, at that stage you will see or we will discuss that what is the use of this resultant. When we are calculating the shear force or bending moment due to any particular load, then we need this resultant. So when we will be analyzing beams, drawing shear force diagram, bending moment diagram, at that point you will see that how this resultant is used. Okay.
सर दूसरी चीज सर ये सर आपने स्पैन्स में डिवाइड किया सर, इसकी क्या सर रीजन बताइए आपने स्पैन्स में डिवाइड करके फिर उसको सर किस तरह किए?
Are you talking about these arrows?
Yes sir, ये जो L/2 है और दूसरे में 2L/3 और L/3.
Oh, this is to show the location of the resultant, that whatever is total magnitude of the load, the resultant of the load, it will pass through, in this case, it will pass through the centroid of the rectangle. What is the location of centroid of a rectangle? It is at half distance from either of the ends. L/2 from this side and L/2 from this side. If we have a rectangle, its centroid is at the center. Okay, so L/2 and L/2. Similarly, height H/2 and H/2. This is the location of centroid. And if we have a triangle, the location of the centroid is L/3 from this end and 2L/3 from this end, if L is the length of the base. Okay. Is it clear?
So second one clear नहीं हुआ sir, 2L/3 और L/3.
2L/3. In both the cases, the resultant will pass through the centroid of the area. If I have a triangular area, its centroid will be here. Centroid is the geometrical center, and the formula, if this total length is L, then the location of centroid will be 2L/3 and L/3 from this side. For example, if this length is 30 meters, let's say, so the location of centroid will be 20 meters from this edge and 10 meters from this edge. And if this one is, let's say, 15 meter, this H, then the location of centroid, this is 2h by 3 and h by 3. So if this h is 15 meters, then this is 5 meters and this is 10 meters. That's the location of centroid, the geometrical center of the area. Does it make sense now?
Yes, sir, it's clear now, sir. But sir, resultant, you said that resultant will pass through the centroid, sir.
Yes.
सर इसका सर क्या मतलब है कि जब हम किसी भी फोर्स लगा रही है तो हम रिजल्टेंट इसलिए लेते हैं ताकि हमें पता चल सके कि ये किस जगह पे मेनली एक्ट करेगा और सेंट्रॉइड में जगह होगी.
Exactly. When we will be calculating the movements, let's say due to any applied load, we will need the location of the resultant. That will help us in defining the lever arm for that force. Okay. As of now, just keep this thing in your mind that the resultant of centroid is 2L by 3 from this edge. The resultant of a triangular load is 2L by 3 from this side and L by 3 from this side. How do we practically use it while calculating shear force and bending moment? We will talk about that in detail. We will be solving a lot of problems about that. So don't worry about that, okay?
Okay, sir. Thank you.
All right.
Sir, likewise, can we say that by converting this uniform bearing load or bearing load, we can convert that into resultant and make it point load?
No, we cannot.
Can this be said as well?
No, the action of a point load and a UDL and a VDL are different on the structure. When we will, although at some point in making our calculations, we might have to consider the resultant of the load, but when we will be drawing shear force diagram, bending moment diagram, we will consider point load as point load, UDL as UDL, and VDL as VDL. Okay?
Excuse me, sir.
All right.
Yes.
सर ये जो आपने VDL बताया, अगर इसमें हिंज स्पोर्ट से स्टार्ट हो और मिडल तक सर इंक्रीज करे लोड और उसके बाद रोलर स्पोर्ट तक डिक्रीज करे, तो सर ऐसा कोई केस हो सकता है?
हाँ, ऐसा केस हो सकता है, and we will probably solve such case. This is a simplified version. The actual loading is most of the time a combination of all of these three. Okay, so we will analyze beams that will have maybe 2 point loads, 1 UDL and 1 VDL, maybe, or anything. Okay, so we are not saying that at one time only one type of load will be present. All right.
Yes, sir. Thank you.
Okay, you're welcome. Now, with this, now let's consider the last two very important definitions: shear force and bending moment. Shear force. Let me turn on the other camera for a minute. Okay, if we have a beam here and it is subjected to transverse load, so this load has two tendencies. One tendency is to bend the member and other tendency is to break the member. The load, when we apply load, it tends to break the member or it tends to slide to camera is on or off?
Sir, now it's showing, but sir, moment ago it was not working.
Okay, can you see me in the picture? No?
Yes, sir.
Yes, sir.
No, sir.
No?
No, sir.
No, sir.
Okay, if some people can see, it means that the problem is not on my end. Hopefully it will be fine. Okay?
Yes, sir. You are visible.
Okay, that's fine. So we have a beam, and when I apply a transverse load on this beam, this load has two tendencies. One tendency is to break the member. And what that tendency is, if I consider one section here, let's say this section, so the tendency of the load is to slide one section relative to the other. It tends to break it, or it tends to slide the section, one section relative to the other. And this tendency is termed as shear force. So shear force is a force that tends to slide one section relative to the other. This action is shearing action, and the force that tends to do that is termed as shear force. So shear force is a force that tends to slide one section against the other, and this shearing tendency may be in two different orientations. Let's come back to paper. Okay.
Repeat it once.
Okay. Shear force is a force that tends to slide one section relative to the other. Shear force is a force that tends to slide one section relative to the other. And there are two possibilities for this. One possibility is that left part of this section tends to move upward and right part of the section tends to move downwards. And this, according to our convention, will be treated as positive shear. This is positive shear. The other possibility is that the left part is downwards and the right part goes upward. This, according to our convention, is negative shear. So shear force is a force that tends to slide one section relative to the other, and if the tendency is like this, that the left part is going up and right part is sliding down, we call this positive shear. On the other hand, if left part has a tendency to move down and right part has a tendency to move up, this is termed as negative shear. Okay, how these positive and negative shears are used in calculation, that we will learn when we will start calculating these shear forces while solving the numerical problems. Okay, and next tendency of transverse load is bending movement. Bending movement. And there are two types of bending moments. If we have a beam and let's say load is acting like this, that load will deflect the beam, this way. And this is termed as sagging. And according to our convention, sagging is positive. The other possibility is that we have a load acting in the upward direction and that causes the beam to bend like this. This is termed as hogging. And according to our convention, hogging is negative. How this is incorporated in calculations, we will discuss that in detail. Let me give you a quick idea what do we mean by this sagging and or by movement. As I said before, that whenever we apply load on the structure, the transverse load, it has two tendencies. I apply load here, one tendency is try to break this member, other tendency is to bend the member. So the movement that tends to bend the member is termed as bending movement. The question is that whether every movement is bending movement? No, every movement is not bending movement. For example, if I have a member like this and I apply movement like this, this is also movement. See, movement is rotational effect of force and this is also movement, but whether this movement is bending movement or not, no, this is not bending movement. This is twisting movement or torque. In this course, Dr. Safir Abbas will be discussing this torque, twisting movement and torsion in detail, and you will learn how to calculate stresses for that. With me, we will be talking about bending. We have a member and when it bends down, what forces are generated and how those forces are calculated and how their variation is studied along the length of the member. So everybody is clear about shear force and bending moment?
Excuse me, sir.
Yes.
Yes,
सर बेंडिंग का तो सर समझ आ गया, लेकिन सर शेयर का सर आप काइंडली एक्सप्लेन करते हैं जरा थोड़ा डिटेल में.
Okay. One member. Just assume that this is one beam. I apply load on the beam. That load will have the tendency to break the beam. Okay. If you apply load, that load has two tendencies. One tendency is to bend the beam. If the load is acting in the upward direction, it will tend to bend the beam. Other tendency is to break the beam. That breaking tendency is termed as shear. and the force, internal force that is generated against that tendency, that is termed as shear force. Okay, and both the shear force and bending moment, this bending moment and shear force, both are internal forces. We cannot see them. It's just like headache. Headache is there, it's pain, you can feel it, but you cannot see that, right?
सर ये
So
इंटरनल सर किस तरह है सर? ये तो क्योंकि सर लोड तो सर एक्सटर्नल है और बैंड भी वो कर रहा है, तो सर फिर ये
load
bending
is
moment
external, but when you apply external load, internal resistance to that load or internal forces are generated, because we have a solid member, right? When you apply load, the member resists that load, and it tends to, and how does it resist? By generating internal forces. So the shear force and bending moment that we are talking about, both are internal forces developed. Okay? The external load is only this transverse force, this point load or a UDL or a medial. But the bending moment and shear force are internal forces which are generated as a reaction to the applied load. Okay? Is that clear?
Okay, sir. Okay, sir.
All right. So with this, we have reached the conclusion of our discussion today. Let me switch the camera, and I will take your attendance one more time just to keep track of the students. Okay, where is the meeting? Okay, so now I've stopped sharing my screen, and let me take your attendance. Okay, it is downloaded. We have only 27 attendees. Why this attendance is so low? Okay, anyways, I'm keeping track of it. Now I will stop recording, and hopefully this recording will be available to you soon.